Okay, so let's talk about 73. The big beautiful problem.
I've had to make to work on this, so we just gotta erase it. What's that? Beautiful.
We're winning.
We're gonna win so much, you're gonna get tired of winning.
All right. So here's the story. We'll take cells constructed with 2 zinc cells. All right. All right. 2 zinc cells. So here's the story.
His handwriting is bad, and then you guys will.
One is 1.8 molar, which is pretty concentrated.
It's gonna be nice.
And the other one is whatever that is, 1.00 times 10 to the minus second.
Yeah.
Okay, so okay, so this is what's known as a concentration cell, and it's based upon the fact that Mother Nature hates things being out of balance. So this only works, number one, when you have, like this wouldn't work if you put copper inside the zinc. So you would have to have strips of zinc inside the zinc nitrate, because otherwise you're going to get reactions with the zinc. Okay? So you just put, just like I did yesterday, you put copper in copper, you put zinc in zinc, you put whatever these are. You still have to have the salt bridge because you're still going to be messing up the concentration. So here's what's going to happen. So Mother Nature says this is bad, okay? We have a discrepancy in these concentrations, and we need to remedy this situation. So what's going to happen to the 1.8 molar concentration? It's going to go down. So what that means over here, I've got to take zinc 2 plus and make it gain electrons to turn into elemental zinc. That's the only way we can do this. Okay? Now, over here, this concentration is too low. So we need to make this concentration go up. So over here, we need to take elemental zinc and turn that into zinc ions, and it's going to give up 2 electrons. So knowing this, which cell, the 1.8 or the lower concentration, is going to undergo reduction?
1.8.
1.8. Okay? So this is going to undergo reduction because of the fact that that's going to take in those electrons. Okay? So what you would see happening over the period of time, you would see if you took the mass of it over the period of time, you would see the mass of that electrode increase because it's called plating out. You're plating out that zinc. Over the period of time, you would see the mass of the other one actually go down. Like if you waited over the period of time, you would see that mass decrease because it's turning into ion. So since the 1.8 molar is undergoing reduction, is that the cathode or the anode?
Cathode.
Yeah. Cathode, the red cat, right? So this is still the cathode, and this is still the anode. Okay? Now, which direction do the electrons flow?
High to low. High to low. Cathode anode. Which is cathode?
Hold on.
Okay.
So this is pulling in the electron, right? This is pulling in the electron. This is giving up the electron. So it's still the same story. You still go from anode to the cathode. Okay? That's still, just like in anything, the electrons always flow from the anode to the cathode. Do they flow through the salt bridge?
No.
Absolutely not. Nothing goes through the salt bridge. The whole purpose of the salt bridge is to do what?
Neutrality.
Maintain neutrality. Okay? So the electrons are still flowing in that external circuit through the cathode. Now, what you want to do is calculate the theoretical value for the voltmeter. So you're going to use that Nernst equation of E equaling E naught minus 0.0592 over N times the log of Q. Now, let's just think this through for just a little bit, okay? So the weird part about this is that zinc is both reduced and oxidized, okay? But think about this. If E naught is under standard conditions, if you had a 1 molar solution of zinc and zinc ions on both sides, if you had a 1 molar concentration on both sides, would there be any voltage at all?
No.
Why not?
Because there's no difference to equal out.
Yeah, there's nothing to balance. It's like, hey, you're at 1 molar, I'm at 1 molar, let's just chill out, okay? The electrons would have no desire to move because everything would be at exactly 1 molar. So your E naught value is going to be 0, okay? So when you're dealing with a voltaic cell situation, if everything is under standard conditions, and that's what E naught means, so if everything was at 1 molar, your E naught value would just be 0. So clearly this happens. So what does your E value have to be, a positive or a negative number?
Positive.
Yeah, so I've got to have a positive E value because it's spontaneous. This reaction took place. We did that yesterday, okay? The reaction takes place. If this reaction didn't take place, it's like, why study it? It doesn't happen. Well, that's not cool, okay? So it has to happen. So your E naught has to be a positive value. So you're going to have 0 minus 0.0592 over N. I screwed that up. I wrote that wrong. Okay, that's 90. Now, what's your N value?
Number of electrons.
Which in this case is going to be 2. Okay, so N is going to be 2 times the log of the 2 concentrations. Okay, so here's the next question. Which do we put where? So think this through. We want a positive E value. So we're going to have 0 minus something. So what's the only way I can end up with a positive value for E? If that side is negative. Okay? But I'm taking the log. So here's the question. Why?
Products ever react less than 1.
Yeah, because I need to take a log of a number less than 1. Okay? So over here, in this situation, I'm going to take 1.00 times 10 to the minus second over 1.8. Okay? Because that's the only way I can produce a positive E value. Now, here's how you can check it if you did this wrong. Let's say that you make a mistake and you put 1.8 over 1 times 10 to the minus second. You punch this into the calculator and the Oracle speaks and you get a negative E value. Right away you'd be going, oh, this is bad. Because I'm getting a negative E value, which would mean that this is non-spontaneous. So you're going to get the same answer. It's just whether or not it's a positive or negative value. But this is why you always put low over high. Okay? So there's 2 ways to remember this. The electrons flow from low to high, and the log is low over high. Okay? Cool with that? Okay. Now, let's talk about 70. So on 70, you've got 4 plus. Okay. So let's start with this. What would you physically see happening if this reaction took place? How could you tell that this reaction took place?
Chromium metal going down and the ions going up.
Beautiful. Because this is elemental chromium. So what you would do is you would prepare the solution, okay? Maybe you have cesium nitrate, Cu4 plus nitrate, and you would drop in a piece of chromium, okay? Solid piece of chromium. And if this reaction happened, it's exactly what Nathan said. Over a period of time, the most visible way to recognize this reaction taking place is that you would see the chromium dissolve. Okay? So, in the redox parlance, when you see in a word description that you see something dissolving, what that means is that the elemental form of that substance was placed in there and it's going to dissolve. So, the first thing you need on 70 is the EMF. EMF is the same thing as your voltage. EMF technically stands for electromotive force. So EMF and voltage mean the exact same thing. Okay? So that answer on 70 should be around like 2.35. Okay? That's just your standard conditions. Boom, that's what you've got. When you hook it up, you're never actually going to see that because it's always a little bit less than that, but that's like the theoretical value of 2.35. Now, so when you look at this, and this is where you have to understand what is happening. Do not just get hung up on the math. Understand the chemistry and why this is happening. So you're going to have two different cells, right? Okay, or in this case, one cell. But here's the story. You're going to have the chromium, right? So what's the chromium doing? Being reduced or oxidized? It's being oxidized, so it's giving up the electrons. The Ce4 plus is gaining those and turning into Ce3 plus, okay? So you're going to see this thing dissolve. If you were to actually hook this up like a cross-voltaic cell, you could put the cesium in here, but typically what's happening with this one is that you drop it in. This isn't typically how you would build a cell. And the reason why this would technically be difficult to build a cell is because when you have Ce4 plus over here, you really can't have like a strip of Ce4 plus, okay? Because it's like an ion. So that's why this would you can talk about like the theoretical side of this, but actually build it would be tough. But here's the bigger idea, is that this thing, the cesium, is going from 4 plus into 3 plus. It's gaining electron. It's still going to exist as an ion, but the chromium is going to dissolve. Nathan.
Why are batteries built out of lithium?
No, can you go in like not like maybe like an athlete?
What were you saying, Mr. Griffin?
Can you continue? Like,
Just look at the
Okay.
chart. Bro, you already know this, bro. Please just look at
The reason they're built out of lithium, primarily because they're small. Sodium is actually much more abundant than lithium
That's
is,
what I was thinking.
but lithium is smaller.
Oh,
So in a given space, you can put a lot more lithium ions than you can sodium ions.
makes perfect.
They work the same, but
Okay.
yeah, because they
So
both
in the
have
near
one
future, we
valence.
might have to convert to image batteries, potentially.
Yeah, but you're probably going to go solid state batteries without being liquids before that point.
Oh, yeah.
Okay, back to our story. So, what's going to happen on 70B is that what's going to happen in the cell under cesium 4 plus goes to 3 molar and the Ce3 plus goes to 0.1. So, what's going to happen is that you're going to overload this concentration. Okay? You're going to make that really big. So, understand that the Ce4 plus is gaining these electrons and turning into Ce3 plus. So from a socioeconomic, not socioeconomic, from no, just a social aspect. Here's what's happening. The Ce4 plus are the people throwing the party, okay? The Ce4 plus are trying to get the electrons in. So they're sending out group chats, videos, whatever, okay, that they record in their 18th chemistry class. And they're going, that literally just oblivious to the whole discussion. I said Ce4 plus is trying to get like electrons to come over. I said, they're sending out text messages, videos that they're recording in their 18th chemistry class, whatever. And you were just like,
oh, okay, like Natalie cheated.
yeah.
I can't.
Anyway,
Yeah, if you're getting reported late.
so,
You're 60% AI.
Dude, oh
oh yeah, we're talking about AI there, big boy. Huh? I'm gonna throw down that card. So from a social standpoint, the CE4 plus are throwing the party. And they're trying to get the Chihuahuas to come over to them. Now, the other side of this is the chromium is turning into CR3 plus ions. So if you look at that first one on conditions of B, you've got a very high concentration of the CE4 plus ions. So what that means is that you have a lot of people trying to pull this in. You have people just full time sending out some type of social media message, okay? Twitter, whatever, okay? Instagram, Snapchat, whatever you do, okay? Now, the chromium has to turn into the ion. What inhibits this is if the CR3 plus is crowded. If there's already a bunch of CR3 plus ions in there, that's tough to do. It would be like, hey, there's a big party out in the hall, but the hall was crowded. And you're going, it might be a good party. I really don't want to go because it's crowded, okay? So here's the setup. You have a whole bunch of people trying to get the Chihuahuas to go. And the hallway is basically empty. So this is a good combination. So from a social standpoint, the voltage is going to go up because you got a lot of people trying to get the Chihuahuas to move, and the hallway is basically empty. That's a winning combination. So if you want to think of it that way, great. Now, mathematically, you're going to have E equals that E naught value, which is 2.35, minus 0.0592. Now, what are you going to use for the value of N?
3.
Why?
The number of electrons that are being
CR3 plus.
Yeah, that's the balancing thing. If you were to balance the half reactions, N's going to equal 3. So you got 3 here. Now, this is what you have to watch. So Q is products over reactants. So this is going to be the concentration of your CR3 plus ion times the concentration of your CE3 plus ions. Now, what do you have to do with the CE3 plus ions?
Q.
Why?
Because it's the 3.
Because there's a 3 in front of it. So you've got to cube that value and then divide that by the concentration of your CE4 plus ions. But what do you have to do with the concentration of the CU4 plus ions? That also has to get Q. Now, so here's what you want to watch. One, when you get to B, they have to give you all 3 of those concentrations. You can't deal with 2, but you have to have all 3. If you want to look at big changes in this, focus on the ones that are cubed. So if you make small changes to the values that are cubed, that has a big impact on the concentration of the value of Q. Now, if you plug in these numbers, okay? So if you plug in these numbers, you get 0.1 cubed, and you get 0.01, and then that one down there is 3, and that's going to get Q. Now, if you're a math nerd, it's like, Burkamp, I don't get invited to a lot of parties. I want to know how the math works, which is why you probably don't get invited to a lot. Because you're better at home with your calculator or playing Warcraft or something. So, mathematically, here's what's happening. Is the Q a big number or a small number? Q is really, really small, which means you're going to be taking the log of a really, really, really small number, right? So when you take the log of a really small number, that makes it a negative value.
Because it's less than 0.
which gets added to the 2.35.
So we get bigger.
So it's going to get bigger. Okay? So I don't care how you explain this trend, but I promise you, you're going to have to explain this. So you can either explain it mathematically and say, hey, there's an inverse relationship between Q and E. As Q gets smaller, you're taking the log of a smaller number, E is going to get bigger. If you want to explain it in terms of social norms, hey, there's a lot of ions asking the chihuahuas to come party, and the hallway is empty, that's conducive to the electrons really wanting to move. Okay, literally, I don't care how you explain it. Okay, now if you're actually taking the AP test, you might not write chihuahuas. They probably don't want to understand that. Use the word electrons, but there you go. Now, when you get to 70C, okay, here's the contrast of what's happening on 70C. On 70C, you've got a really, really, really small concentration of your CE4 plus. And this is like the opposite. So what's happening on 70C is that you have like one person sending out a text message going, hey, big party out in the hallway. And you go to the hallway and you look, and the hallway is crowded. It's like, this is just, I really don't have any desire to go. Okay? There's not a lot of people sending out the message. The hallway is already crowded. I really don't want to go. If that speaks to you, there's that. Mathematically, what happens to your value of Q?
It goes up.
It goes way up.
Because you divide by small number.
So now Q is a really, really big number, and now you're taking the log of a really big number, which is a positive value. So now you're going to take 2.35 and subtract that, which is going to make your E naught value get smaller. So on 70, all of your answers on 70 should start with a 2. Okay? The biggest one should be B. That should be around 2.5. Your answer to 70C should be around 2.2. Okay? What?
I think for our sheets it's different. It's like I didn't get 2.25. I had 2.45.
Yeah.
Oh, I got that also.
You
got it?
That is because
This sheet
one,
and that, or whatever you did,
Back in the
we got two different
As
things.
long as I can see the math.
Cool.
Yeah.
That's the biggest
So
thing.
if I start making up numbers, but I have the right
You
sort of
won't know.
calculations.
You won't know. You won't know.
Adam,
Get him in the ballpark.
You're poking the bear.
do you want us to just put what
Adam,
she
the numbers have
got?
to be so much close to.
No, there's only two
I'll
possible.
make every number.
So,
You value.
You're so funny.
so the other thing is that when you get to like question number 68, and that 68B, the size of the aluminum electrode is increased. Okay? If you change the size of the aluminum electrode, what impact will that have?
The answer is no change, but it's just no. I'm not seeing it.
Okay.
Because I know it's about concentration.
So here's the question, Nathan. Where in these equations can you plug in the surface area of
Even
the
not
electrode?
nowhere. No variable.
So this is what's known as an intrinsic property. So as long as you have some amount of it there, the reaction's going to take place. So whether you have an aluminum that's like a toothpick, or you have one that's an inch wide, doesn't matter, because you can't plug that into the equation.
I just think that's weird.
Sorry.
Nobody used to ask.
It's like if you look at cells, you know, there's small areas doing cells. You know what I mean?
But it's still the same electrical potential.
Yeah.
Because it's basically potential per electron.
Big myth fan, huh, Mike?
What's this guy adding here?
Big myth of-
Michael, I think this is placed today. Michael, I can't see your screen.
Okay, any questions on that assignment?
Oh, you got it.
Going once, going twice?
Wait,
It's fancy.
is 68
Wait,
also no change? Because you have to
I was ready to go. Unlike I said.
But then is D increased?
Well, let me write my name on it first.
So,
Oh,
on
you
that
can-
one, let me give you a hint.
Thank you.
You're decreasing
Oh,
the
and then-
concentration
What?
of
John's not
silver
finished.
ion. Okay, so that one you do change the concentration.
I think it's decreasing.
I'm just telling you, but you're gonna change it. Okay, all right, good? Stop, yeah.